Hi everybody, hope you're doing well. This video here is going to walk you through the fourth section of Unit 8, which is going to introduce you to logarithmic functions and talk you through some of the basics of them. This video is going to be very important for a lot of the lessons we're going to be doing in future sections, so you're definitely going to want to pay close attention to the different things I'm going to work through here throughout the lesson. You'll notice up on the screen I've got the graphing calculator already handy. I'm going to also show you how to use several different features on your graphing calculator in this lesson, so before you get started you might want to make sure you have that handy. So let's first talk about what is the point of a logarithm. Basically, a logarithmic function is used to help solve for an exponent. So you've learned how to solve for a whole bunch of different things algebraically, but the one thing you really haven't solved for is if your variable is an exponent, how do you find that? Well, the way that you find that is to use a logarithmic function. Logarithms are the inverse of exponential functions, which is what we've talked about in the last three lessons. So you're going to see a lot of flipping back and forth between those two types of functions as they are inversely related. So what we're going to walk through here are several different things. We're going to first talk about how do we flip between the two formats. How do I go from a logarithm to an exponent form and vice versa, because that's something you're going to use a lot for equation solving and for inverse finding. We're also going to take a look at how do we enter some of these things on the calculator to do some basic evaluation and computation. And then last, we'll finish off with how do we find some inverses of logarithmic and exponential functions, once again reinforcing how we can go back and forth. So you can see from the box at the top here how we read logarithmic functions. So you see log base b of y equal to x. That base b is the same as the base b of an exponential function. The x is what the logarithmic function is equal to, and that x would represent the exponent. The y is what would happen if I took the base risen to the exponent power. So what we're going to look at here first is how do I flip between the two forms? How can I turn a logarithm into an exponent, and how can I turn exponential form into logarithmic form? So why don't we take a look here at the first set of examples here, A, B, C, D. So A and B, I have logarithms written out. So in A, I have log base 2 of 8 is equal to 3. What I'm going to do is convert it to exponent form. So the base of the log is the same as the base of exponential form. So in this case, I have a base of 2, which means I have a base of 2 for my exponent form. The 3 is what the exponent is, because the logarithmic function is set equal to the exponent. So in exponential form, that means the 3 becomes my exponent of my base, which leaves me with what it has to be equal to, in this case the 8. So log base 2 of 8 equal to 3 is the same as saying 2 to the third power equals 8. One thing you'll notice, especially if you're going from log form to exponent form, if you're trying to, especially initially here, to arrange the numbers, I certainly don't want you playing a guessing game, but when you look at the exponent form, you should be able to look at it and go, oh yeah, 2 to the third power is 8. If you put the numbers in the wrong spot, you'll get an equation that doesn't make any sense. So that's just something you can keep in mind as you're moving things around. Same thing here in B. I've got log base 4 of 1 equals 0. The base of the logarithmic function is 4, so that's going to be the base of my exponential function. The log function is equal to 0. It's always equal to the exponent, so that means the exponent is 0. And then it has to be equal to the final value remaining, which is the 1. 4 to the 0 power, if you were to punch that in, is definitely equal to 1, so I definitely have it in the right order. Now C and D, I'm going to go the opposite way. I have exponential form. I'm going to go backwards and put it into log form. So 12 to the first equals 12. Well, I have a base of 12, which means the base of my logarithmic function has to be 12. It's set equal to the exponent, so I'm going to set it equal to 1, and then whatever I have left over, that's the number that's going to go here in the middle before the equal sign. So I'd read this as log base 12 of 12 equals 1. And same thing in D. 1/4 to the negative first power equals 4. So again, the base of my exponent function is the base of my logarithmic function. So I'd have log base of 1/4 to the 4 equals my exponent, negative 1. That's how you flip back and forth between the two forms. You can kind of see with the variable notation up in the top, and if that works for you, terrific. If it doesn't, you can certainly do whatever it is to help you memorize where the numbers go. But ultimately, what I'll be showing you here in a few minutes is how you can punch this in the calculator, and it'll also serve as a great way to check your work. But ultimately, it is important to know where the values go, because as you'll see in a little bit, we'll have variables involved, and ultimately your calculator can't quite save you if we start throwing in some x's. So, a couple of things to keep in mind. There are some special logarithm values, which are kind of common sense if you manipulate things correctly, because you have in the first one here what's called a logarithm of 1. Log base b of 1 is equal to 0 because b to the 0 equals 1. We saw that with the first example here in option B, or problem B, I should say. Anything to the 0 power is 1. So if I have log base of anything of 1, it's going to equal an exponent of 0. Same thing here with logarithm B with base B. Same thing. If I see the numbers repeat twice like that, so we saw that in example C, where we had log base 12 of 12, that's going to equal a power of 1, because anything to the first power is equal to itself. There are a couple of special logarithms that you will come across. One's called the common logarithm. So, we've learned earlier in the year about when we had common roots. When we had a square root, we didn't see the 2 there because it was implied that if you're taking a root and there's no number, it's a second root. Same thing here with logs. If you are taking a log and you do not see a base, it is the same as having a base of 10. So in the world of logarithms, if you don't see a base, it is essentially the same as taking a base of 10. We have what's also called natural logarithms. So this is going to use what we talked about a couple lessons ago with the natural base. The natural base is e. So a logarithm with base e is notated with this ln, okay, which is a way of saying natural log. The reason why the letters are backwards is because in Latin it's actually known as something to the effect, I believe, of like logarithmic natural or something like that. It's just actually taking the two words and putting them backwards. I think I botched the Latin on that, but that's not the point. The point is if you see ln, that means you're dealing with a natural log that's involving that natural base of e. Now, what I'm going to show you with these things is how to use them here in the calculator, but also how you can use them with a bunch of different properties, equations, and stuff over the next few lessons. So why don't we talk about first here how we can evaluate using the calculator. So I'll give you two expressions here at the bottom. We have log 8 and natural log of 0.3. So this is now where we're going to use our calculators and start punching stuff in. So let's go ahead and do that. So if I want to find log 8, all I need to do on the calculator, the log button should be next to the 7. All you have to do is hit log 8. Most of the time when you find logarithms, now there are certain numbers where they'll come out really nice, but a lot of the times you're going to get these gross decimals like we've seen in a lot of the other problems that we've done in this unit already. When you type them in, if you get a decimal, totally fine. All you want to make sure of is when you write your answer that you go to 3 decimal places just to be a little bit more accurate with your answer. So in this case, all you have to do to find log 8, you hit the log button, type in the 8, and it'll spit out your answer, which in this case is 0.903, so on and so forth. So, if you're finding just a regular log, all you gotta do is hit the button, type in the number you're finding log of, boom, you'll get yourself your answer. If I want to find natural logs, so if I see this ln, all you have to do to find natural log is you'll see underneath the log button, a button that says ln for that natural log. All you have to do is hit that, type in the number that you're taking the natural log of, and again, it'll spit out an answer for you. So again, it will more than likely, well, especially with natural logs, you will most likely get a gross decimal of sorts. Again, take it to 3 places. So again, for your keystroke for that, you're just hitting the LM button, which again is next to the 4. Type in your number and your answer, which will round to negative 1.204. So your calculator is going to be very helpful when you're doing some basic computation and evaluation, and that's how you're going to use it to find common logs of numbers or the natural log. Now, as you've probably noticed, and if you haven't, that's okay too, if you look at the examples from up top, we had logs that had different bases. Okay, we had a base of 2, a base of 4, base of 12, base of 1/4. What do we do to find logs that have different types of bases? Let's take a look here at the next page and find that out. So, if we go ahead and take a look at the next page, we're going to look at something called the change of base formula. And what this is this is going to talk us through how to find and evaluate logarithms that have bases that aren't the common base, which again is 10. So in order to do that, all we have to do is this. To find anything log base c of a, all you have to do is take the common log of a divided by the common log of c. So I'm going to show you what this looks like here, and you're going to see the same thing for all 4 examples. So again, once you see 1 or 2, follow the template, see if you can solve it from there. So with each of these, I'm going to set them up the same way. So with example A, I have log base 4 of 64. All I'm going to do there is take the log of 64 divided by the log of 4. All you will then do is go to your calculator and type that in. So I know I'm going to lose this off the screen here for a second, but now I'm going to go ahead and type that in. So you can use your fraction button if you want. You can simply just hit division. It's totally up to you. I'm going to go ahead and use the fraction button because I can. So I'm going to have log 64 on the top over log of 4. And this will give me the answer of 3. Now, some of these you're going to notice come out actually very nicely depending on your combination of numbers in the logarithmic function, because you might get very nice clean exponents. Ultimately, when you're evaluating a log function, you're finding the exponent that it's equal to. So think of it this way. If I were to write this back out, so again, if I'm just solving it here and evaluating, log 64 over log 4 is equal to 3. Keep in mind, tying it back to what I showed you on the last page, log base 4 of 64 equal to 3 is the same as 4 to the third equals 64. So some of these, if you're good with your basic exponents and rewriting these problems around, you might be able to figure them out without having to compute them. Most of the time, you probably will need a calculator of some sort, because a lot of these will not come out super clean. But ultimately, some of these are very nice combinations that have nice whole number integer answers. So, using the same template here for B, C, and D. So for B, if I'm going to find it, I'm going to have log of 0.2 over log of 5. C, I'm going to have log of 125 over log of 1/5. And then D, log of 6 over log of 36. Now, one thing you want to keep in mind as you're doing these, don't accidentally make the mistake of, oh, I'm going to cancel log and then just divide the two numbers that are there. That's not the math that's occurring here. What I'm showing you is exactly what needs to be entered into the calculator. So, what I would suggest is hit the pause button here real quick, copy this formatting down, and then we're going to go ahead and punch all 3 of these into the calculator, because again, once I switch back to the calculator, I'm going to lose them off the screen. So, with my 3 functions here in B, C, and D, let's go ahead and enter it in. So this is for B. So we're going to take log of 0.2 divided by log of 5. And that gets me an answer of -1. I'll copy that down here in a second. For C, same deal. I'm taking log of 125 divided by log of 1/5. Now, you can go ahead and use your fraction button to enter that in. I'm just going to enter that in as 0.2 because I know it's the exact same thing. And that gets me an answer of -3. And then last but not least, for D, log of 6 over log of 36. And that gets me a final answer of 1/2. So again, every time I'm evaluating these, I'm basically finding what is the exponent that ties these two values together, what ties the base and the answer that we have. So again, just to re-put all this stuff down here, we've got -1 as my answer for B. For C, we've got an answer of -3. And for D, we've got an answer of 1/2. So again, depending on the combination of numbers, you might be able to figure them out mentally if you can figure out what's the missing exponent in the middle of putting those two numbers together in the problem in exponential form. But ultimately, your calculator will help you evaluate these immensely as long as you don't have to mess with any variables. So again, if you're finding an answer to a problem that has a different base for log, so basically anything other than 10, this is your process to go about that. So that is something that you're definitely going to need as we move forward, especially into equation solving and the sort. Last thing we're going to take a look at here is we're going to take a look at inverse functions, which is going to tie together what I referenced in the beginning of how to manipulate between exponential and logarithmic forms and how to flip back and forth with these. So what we're going to take a look at here is how to find inverse. So there's a lot of math speak here in the middle. Basically, if I want to find the inverse, if it's written in logarithmic form, I need to make it in exponent form. If it's written in exponential form, I need to turn it to logarithmic form. Before we worry about that, let's talk about how to find the inverse of a function in general. This is something you learned how to do in the last unit, and it's going to incorporate a lot of these same exact skills that you've already learned. So if I give you a basic function here like y equals x cubed minus 4, and I say go find the inverse, first step that you want to take, and again, if you think you can solve this here before I go through it, feel free to try it and then check the answer here in about a minute after this point in the video. But if I am trying to find the inverse, first thing I'm going to do, flip my variables. So the x and y are going to change spots, and I'm going to have x equals y cubed minus 4. None of the signs change, the numbers don't move, it's the variables that change places. Once I do that, to find the inverse, I need to rework the problem to get the y by itself. So the way that I'm going to do that takes two steps. I'm going to add 4, so it gets me to the y cubed, and then I'm going to cube root each side. Once I do that, cube root of x plus 4 equals y is the inverse of the original function I started with. We're going to use those same skills for all the examples in number 4, A through D. The thing is, it isn't quite as basic as seeing some of these basic operations where if I see addition, I'm going to subtract. If I see a cube, I'm going to cube root. There may still be some of those elements, but ultimately the big emphasis is, hey, if I see a logarithm, I need to rewrite it as an exponent. If I see an exponential form, I need to rewrite it as a logarithm to help get the y back by itself. So we're going to walk through these 4 examples here, and again, watch these very carefully here to see how I'm moving all the pieces around. So for A, I have y equals log base 4 of x. Goal here is to find the inverse. I'm going to switch the two variables. So I'm going to have x equals log base 4 of y. Now, the goal is to get the y by itself. So looking at this here, we're not going to divide by log base 4. That's not a thing you can do. There's nothing else surrounding it. I don't see it being multiplied by anything. I don't see anything else. It's written in logarithmic form with no random attachments. Only thing I can do from here is to turn this into exponential form. So what I'm going to do is to turn it to exponential form. The base of the log is the same as the base of the exponential form. So base 4 means I have base 4 of my exponential form. The logarithm is equal to the exponent. Therefore, I'm going to put in my exponent as x. And then that has to be equal to the final value left over in my logarithm function, which is y. When I go from log form to exponential form, I get the y by itself, therefore getting my inverse. So the inverse of y equals log base 4 of x is equal to, is the same thing as, is the inverse of 4 to the x equals y. I'll go down to C so you can see another log being turned into an exponential form to find the inverse. If you want to give it a try, again, hit pause, fast forward a little bit, see if your answer matches up. It's the same deal here. I'm going to switch where the variables go. So I'm going to turn this into x equals log base 3 of y minus 5. It's important that you keep the parentheses around it because that says that y minus 5 is directly attached with the logarithmic function. Without the parentheses, it's kind of saying the minus 5 is just kind of randomly thrown on at the end. So there is a big difference in whether or not there's parentheses there. Now, the whole thing is written as a logarithmic function. There's nothing being randomly multiplied out in front, added or subtracted in back of it. So the only thing I can do to try to get y by itself is to, again, turn this into exponential form. So my base of the log function is 3. Therefore, that's the base of my exponent function. My exponent is x, because that's what the log function is equal to. And I'd set that equal to what's left, the y minus 5. Now, very similar to what I did up above, the only difference is I don't quite have y by itself yet. Not a big deal, though, because this is now where it gets a little bit easier. To get y by itself, all I'd have to do is add 5. So 3x plus 5 equals y is the inverse of my original function. Y equals log base 3 of x minus 5. So again, to find inverse of a log function, it's going to turn into exponential form. Key is, make sure you flip your variables first in order to attempt to get the y by itself. Now B and D, we're going to do the inverse of what we did in A and C. These functions here in B and D are written in exponential form. So ultimately, to find the inverse of them, we're going to have to turn them into log functions. So again, first thing, in B, I'm going to switch my variables. Again, there's nothing being multiplied out in front of the exponential term. There's nothing being added or subtracted or divided or anything else in the way. So the only thing I can do to try to get that y by itself is now turn the exponent form into logarithmic form. So, to do that, again, the base of my exponent function, the 6, is the base of my log function. The exponent is what the log function has to equal, and the remaining value goes directly attached to the log base 6. I now have my y by itself, and I've got my final function. So the inverse of y equals 6 to the x is the function of log base 6 of x equals y. D, same idea. If you want to give this a try, now's a great time to hit pause. If not, follow the example here. So again, exponential form, swap the variables. Again, I look at this function, I don't see anything multiplied to the exponential term, I don't see anything divided by it, I don't see addition or subtraction after the exponential term. The only way to try to get that y by itself is to rewrite it as a log. Now in this case, I know there's a plus 1, but that's part of the exponent. That whole thing has to stick together for right now. I can't just subtract 1 off the bat because that plus 1 is part of the exponent. That would be very bad PEMDAS, and you certainly can't do that. At least not yet. So, only thing I do now is rewrite this in log form. To do that, again, the base of my function is a 3. So the base of my log function is going to be a 3. It is equal to my exponent, which is y plus 1. My remaining value is at x. That's going to get directly attached to log base 3. So, very similar to what we have up above, and very similar kind of the example in C, where there's still a little bit more attached to the y. In order to get the y by itself, I'm going to subtract 1. So I'll have log base 3 of x minus 1 equals y. Now, you'll notice there's no parentheses around it, which means the minus 1 comes after the log function. If I put parentheses, that means I'm grouping with the x, and that has a completely different meaning. So again, inverse turning that exponential into a logarithmic function, y equals 3 to the x plus 1 power. The inverse of that would be log base 3 of x minus 1 is equal to y. So this is definitely new stuff here. It's definitely playing off of things that you have learned previously, but ultimately you need to practice how to use log functions. This is something we're definitely going to see a lot more of here and will prevail throughout the majority of what's left here in this Unit 8, which we still will spend several days on over the next few weeks. I highly, highly suggest, especially with this, since this is so new, definitely attempt the extra practice that has been given to you in the 8.4 folder. Try that compared to the answer key. If you're getting stuck, ask me questions, get a hold of me so we can figure some things out before you attempt the graded assignment. Again, as a friendly reminder, when you submit that, I'm probably going to end up grading it very quickly. So once you do submit it, that's it. That is your attempt with it. So please make sure, if this is something that's confusing you, if you have questions, please get a hold of me at some point during the week, and I'll be more than happy to help you. As always, shoot me an email, send me a Schoology message, or if we need more time, we'll sit down over Zoom and we'll hammer things out. Thanks for watching, and we'll see you next time.